Welcome. In this session, we'll discuss node analysis technique in AC. Okay, so let's start with an example. We draw a circuit. And the circuit is capacitor, inductor here. Then we have resistor and a dependent source. Okay, so what are the values? This is a current source here. Value is 10 cos 10t amperes. Resistor value is 1 ohm. Capacitor is 1 by 10 farad. Inductor is 1 by 10 ohm. 1 by 10 Henry. Sorry. And resistor is 1 ohm here. Then we have a voltage controlled voltage source here. And this Vx is given here. Okay. And our goal is to find V1 node voltage V1 and V2. Okay, let's start. So our goal is to find V1 and V2. What are the values of V1 and V2 in this circuit? Okay, so in this circuit, what we'll do, we'll do node analysis. But first, what we'll do, we'll convert this in the phasor form. So what we do in AC analysis? We convert the circuit in the phasor domain. Then we do the analysis. Okay, so let me draw the phasor equivalent of this. So phasor equivalent of this will be current source will be replaced by a phasor equivalent of. Similarly, this resistor will be replaced by its phasor equivalent. Capacitor will be replaced by its phasor impedance or phasor domain impedance. Same thing we'll do for inductor. Then we have a 1 ohm resistor. And then a dependent source. Let me write the values here. So 10 cos 10t will be written as 10 at an angle of 0. Why 0? Because there is no phase in this source. So 1 ohm will be replaced by 1 ohm. Vx will denote by capital letter now because we are writing it this in phasor domain. 1 by 10 farad will be replaced by what? 1 by j omega c. How much is omega? Omega is 10. You can check from this. Omega is 10. So this will be 1 by j 10 into 1 by 10. 1 by 10 and 10 cancels. So this will be 1 by j. 1 by j is simply minus j. Okay. So this will be replaced by minus j. Then we have 1 by 10 Henry. 1 by 10 Henry will be replaced by I j omega L. J omega L for this is 1 by omega is 10. L is 1 by 10. 10 and 10 cancel. So this will be j. Then we have 1 ohm resistor and we have 3 Vx. Okay. All right. So our goal is to find V1 and small v1 and v2. I will write small v1 and v2 as capital V1 and V2, where V1 and V2 are phasor equivalents of small v1 and v2. Okay. Now, if you look at the circuit, how many nodes are there? 1, 2, 3, and 4. Now, this one we refer as the reference node. And our goal is to find, is this current or voltage? Current. Okay. This is a current source. Okay. So what we'll do? Now, what we have to determine V1 and V2. So first, we'll write the KCL at this node. and then KCL at this node. So if we call this node A and this node B and write KCL at node A and A, how many branches are connected to this node? 1, 2, and 3. And we'll assume all the current in this currents are either leaving or, and now you can see the source current is entering this node, and we'll assume the other two are leaving. Okay, so we'll apply the KCL. KCL at this node will be sum of entering currents will be equal to the sum of the leaving currents. There is only one entering current, so entering current is 10 at an angle of 0. That will be equal to the leaving currents. How many leaving currents are there? 2. What is the current leaving through this branch? It will be uh, voltage divided by impedance. What is the voltage on this node? V1 minus 0 divided by 1. Similarly, what will be the current leaving through this branch? Potential difference across this capacitor divided by the impedance of this capacitor. So it will be V1 minus V2 divided by minus G. Now, why me V1 minus V2? Because we are assuming current is leaving in this direction. Okay, that's fine. So V1 is at higher potential. So let us simplify this. Let me write this in the rectangular form. Now 10 this at an angle of 0 is simply 10 cosine 0 plus j 10 sine 0. Now that will be simply equal. So if I convert it in the rectangular form, it will be 10 cosine 0 plus j 10 sine 0. This is the rectangular equivalent of this. Okay. The rectangular equivalent of this is this. Okay. So V1 divided by 1, that is V1. Now this is V1 minus V2 divided by minus J. So if we do rationalization of this, it will be on the numerator side. If I do rationalization of this, J by J, so it will be J and J will be J square, minus minus is plus. So it will be J into V1 minus V2. Okay, we simplify this term. Okay. If we So 10 cos 0 is 10 plus j sine j 10 sine 0 is 0. So it will be simply 10. 10 is equal to V1 plus j V1 minus j V2. Please check the calculations yourself. Okay, this is our equation 1. Now we'll write the KCL at node B. How many branches are connected to this node? 3. So we'll assume all the currents are leaving here. So we'll assume this current is leaving this way. This current is leaving like this, and current is leaving this. So at this node, we'll assume all the 3 currents are leaving. What is the current leaving through the capacitor? It will be V2 minus V1 divided by G. So sum of KCL at node B. Okay, so V2 minus V1 divided by minus J. Why V2 minus V1? Because we are assuming current is leaving from B2 towards A. So V2 is at node B is at higher potential. So 2 minus V1 divided by minus J is the impedance. Then in this direction, this is V2 minus 0 divided by J. So V2 minus 0 divided by J. Reference node has 0 potential. Then V2 minus, what is the potential on this side of this resistor? 3Vx, right? Because the potential on this side is 0. So potential at this node will be simply 3Vx. Okay. So this will be V2 minus 3Vx divided by 1. This is equal to 0. We simplify this. We'll simplify this, rationalizing this. So multiplying this by J and J on the numerator side. Similarly, multiplying this. So what we'll get? So J and J will be minus 1. J square is minus 1. Minus minus is plus. So this will be simply J V2 minus J V1 plus J and this will be in the denominator side. It will be J square. J square is minus 1. So it will be simply minus J This will be simply minus j v2. Please check these calculations one more time. v2 minus 3vx is equal to 0. Let's see if we are able to combine some terms. So this and this cancels. This and this cancels. Please check the calculations. So we are left with minus j v1 plus v2 minus 3vx is equal to 0. So this is our equation 2. Now if we look at, we have two independent equations, but three unknowns. There is also Vx. Can we substitute Vx here? Now if you look at Vx is same as V1, right? So if we this check Vx here, Vx is same as V1. So Vx here is same as V1 because Vx is across 1 ohm and V1 is also across this 1 ohm resistor at node A. So if we substitute this in equation 2, we'll get minus jv1 plus v2 minus 3v1 equal to 0. So let's write the value of, let's transfer these terms on the right hand side. So we're left with v2 will be equal to minus 3v1 will be plus 3v1 minus jv1 will be plus jv1. So this is our equation 3rd. Let me write it like this. Let me take this v1 first common. So this will be equal to 3 plus j v1. So this is our equation 3. Now substituting the value of v2 in equation 1. So if we substitute equation 3 in equation 1, we get 10 is equal to its equation 1, v1 plus jv1. v1 plus jv1 my v1, this is v1. Then we have minus jv2 substituting v2 equal to this. So what we'll get from this? So 10 equal to v1 plus jv1 minus j 3 plus j v1. So this will be equal to v1 plus j v1 minus 3j v1. J and j square, that is minus 1, minus is plus, so v1. Okay, so this will be twice v1 plus jv1 minus 3jv1, that is minus 2jv1. So if we take v1 and 2 common, we are left with 1 minus j v1. So what will be v1 equal to? v1 from this equation is v1 from this equation will be simply 10 divided by 2 into 1 minus j. So if I simplify this, this is simply 5, 1 minus j. Now we'll write this in polar form. So this will be simply 5. What is the polar equivalent of 1 minus j? Polar form, this will be 2 under root of 2 at an angle of tan inverse minus 45. Please check the calculations. We can write 5 as 5 at an angle of 0. Okay, 5 can be written in the polar form as 5 at an angle of 0. So what is the equivalent of this? Please check these calculations one more time. So 5 divided by under root 2, how much is this? 5 divided by under root 2 is 3.52. 3.535 at an angle of 0 minus 45, that will become plus 45. So this is V1 in the phasor form. This is the phasor equivalent of this voltage. Now we can write this. This is the phasor equivalent of our node voltage. Okay. Similarly, what will be V2? So what's V2? V2 is equal to this from equation 3. If we substitute this V1, if we substitute V1 into equation 3, So V2 will be equal to, what is V2 again? 3 plus j V1. 3 plus j V1. For V1, we'll substitute this 5 into 1 minus j. So this will be 3 plus j divided by 1 minus j. Okay. Into 5. I think it is 5. Yes, 5 divided by 1 minus j. Okay. So we can write this as 5 into 3 plus j divided by 1 minus j. Now this is in rectangle form. We'll convert this in the polar form. Please check these one more time. Okay, since V1 is already here in polar form, so let me use the polar form instead of this. Then we need to do only one calculation. So this will be 3 plus j. What's V1? This is V1. V1, then V1 instead of V1, I write 5.355 at an angle of 45 degrees. So what is the polar equivalent of 3 plus j? 3 plus j is, I think, 3 plus j. Please check the calculations. That is 9 plus 1, that is 10, 3.16 at an angle of 18.43. Tan inverse 1 by 3 is 18 multiplied by 3.535 at an angle of 45 degrees. So multiplying these two, we'll get V2 as V2, I think, is 11.18, 3.16 multiplied by 3.535 at an angle of, these two angles will add 18 points. This is 63.43 degrees. So this is the phasor equivalent of V2. So what we have found? We have found the phasor equivalent of V1 and V2. What's V1 equal to? V1 is 3.535 at an angle of 45 degrees, and V2 is 11.18 at an angle of 63.43. Please check these calculations one more time. So if we have to convert back this voltage in the time domain form, so V1 of t will be equal to, simply amplitude is 3.535 cosine of, because our this signal is how much is it? Cos 10t. So we'll write it as cos 10t plus 45 degrees, and V2 is, amplitude of V2 is, let me write V2 of t. V2 of t is simply 11.18 cosine of 10t plus 63.43 degrees. This is in volts. This is in volts. So this is the answer. So we have found the node voltages in the circuit, both in polar form and in time domain form, or in phasor form or time domain equivalent of this. Okay. All right. So we have found the node voltages of this circuit. Okay. Now let's solve one more problem based on this nodal analysis. Okay. We write one more example here. Voltage source, and then resistor, inductor, plus minus. There is a capacitor here, and this is, now let me write the values. This is again a voltage source. So what's the value of this? Now we are given the phasor equivalent of the circuit. We are not given the time domain equivalent of the circuit, but directly the phasor equivalents. Voltage source is 20 at an angle of 0. And then this is minus J, and this is 1 ohm. And our goal is to find phasor voltage V1, phase voltage V1 and V2. Minutes node voltage is V1 and V2 here. Now, if you look at this question closely, we cannot apply the nodal analysis at this node or this node. Why not? Because there is a voltage source in between. Okay, so in order to find the nodal voltage and to apply the nodal analysis is based on KCL. So we need to find the KC in this current in this branch, which is unknown here. Okay, that current is unknown here. So we cannot resort to the ordinary nodal analysis here. Instead, what we do, we introduce a concept that is referred as a supernode. That is referred as a supernode. Why we first of all introduce the concept of supernode? Because we cannot use ordinary node analysis that is based on KCL, because the branch current in the 20-volt source is unknown. So how do we resolve this problem? We introduce a concept that's called a supernode. What's a supernode? Supernode is a combination of two or more than two nodes. So we say this is not a single node, but instead this is a supernode. Supernode is a combination of two or more than two nodes. So this is single node. We treat this as one node. Okay, we consider this as one node, and that node, this node is referred as a supernode because it's a combination of two nodes. Now, so we'll treat this like an ordinary node, but we'll say this is one single node. So how many branches are connected to this node now? You can look at this: one branch, two branches, three branches, and four branches. So sum the four branch currents like we use it to do in the ordinary node analysis will give us the KCL equation at this. Okay. So how many nodes are, how many branches are connected to the super branch? Four branches. So we'll sum the four. So KCL at this super node. So how many branches are there? Four branches. Let us sum the four branch currents. Let's assume all the currents are leaving. Let's assume this current is leaving this way. This current is leaving like this in this branch. This current is leaving like this. And this current is leaving like this. So we are assuming all the currents are leaving in this branch. So let's apply KCL. So what is the current flowing here? It will be V1 minus 10. Okay, V1. What is the potential difference across this resistor? V1 minus 10 at an angle of 0 divided by 1. Similarly, this will be V1 minus 0 divided by J. Plus, what is the current flowing here? So it is V2 minus 0 divided by minus J. Then it will be, what is the current flowing in 1 ohm resistor? V2 minus 0 divided by Y. 1. This is equal to 0. Sum of four branch currents equal to 0. What is the meaning of this 0? This is the voltage of reference node. Okay, this is the voltage of this reference node. All right. So let's simplify this. In order to simplify this, what we'll do, we'll multiply this equation both sides by minus J. So if we multiply this equation by both sides by minus J, we'll get minus J V1 minus 10 at an angle of 0 is simply 10 plus when we multiply both sides for this minus J, this will be minus V1. J and J will cancel. Minus J and minus J will cancel. We are left with V2 plus V2. What will be this? Minus, this will be simply minus JV2. Okay, please check the calculations one more time. Multiplying both sides by minus J, we'll get this expression. So this will be simply minus JV1 plus 10J minus V1 plus V2 minus J. V2 is equal to 0. So let's combine the terms. We have this one V1 here. So let's take V1 common. So V1 will be 1 plus J. Then we have V2. Let's take 2 common, and 10J will be equal to minus 10J on right hand side. So this is our equation. All right. So we'll say this is our equation 1. Now, this is equation 1. Now, there are two unknowns in this equation, so we cannot solve it directly. We need one more equation. How we going to get one more equation? One more equation we'll get from the super node itself. How? If we look at the voltage source, right? What is the voltage on, what is the voltage here? V1, what's the voltage here? So V1 minus V2 is equal to 20 at an angle of 0. How? Because the potential difference across this branch is V1 minus V2. That's equal to 20. Now, why V1 minus V2? Because plus is on the V1 side. So we'll write V1 minus V2 is equal to 20 at an angle of 0. 20 at an angle of 0 is same as 20. So we'll write V1 is equal to 20 plus V2, because 20 at an angle of 0 is simply 20. So substituting the value of V1 in equation 1, we'll get what we'll get from this. So minus V1 will replace with 20 plus V2, then 1 plus J plus V2 into 1 minus J is equal to minus 10J. Let's simplify this term. So it will be minus 20 minus 20J, and then minus V2 minus J V2. Please check the calculations. Here it is V2 minus J V2 is equal to. Now, if we take this on the right hand side and simplify this term, so minus V2 and V2 is plus V2 is gone. So minus JV2 is minus 2JV2 is equal to 10J, and plus 20 plus 20J. So what will be V2 equal to? V2 will be equal to 10J plus 20J is 30J. So this will be 20 plus 30J divided by minus 2J. Please check the calculations one more time. This will be V2. And if we divide the numerator and denominator by 2, this will be 10 plus 15J divided by minus J. So if you multiply numerator and denominator by J, so minus minus is plus, so this will be 10J minus 15, because J and J is J square, that's equal. So this is our V2. This is the V2 in rectangular form. We can also convert it in the polar form. How? We can say the magnitude of this V2 is under root of 100 plus 15 square. Please check the calculations. So that is 18.02 at an angle of minus 15 divided by 10. So this is minus 56.309 degrees. Please check the calculations one more time. So this is the voltage V2 in polar form. Similarly, to get V1, what's the relationship between V1 and V2? V1 is 20 plus V2. What is V2? So V1 is 20 plus V2. We're substituting the value of V2. So this will be 20 plus 10J minus 15. So how much is this? 5 plus 10J. Please check the calculation. So this is the answer in rectangular form. This is the voltage V1 in rectangular form. We can convert it into the polar form as V1 will be simply equal to, what is the magnitude of this? Magnitude of this is simply 11.18 at an angle of tan inverse 10 divided by 5. So this is equal to 63.43 degrees. This is the phasor voltage in polar form. Okay, we don't need to convert the time domain form. Why? And we cannot do that here. Why? Because we don't know the frequency. We don't know the frequency of the source, or we don't know what was the source in time domain. So we'll keep the result in this. Okay, so I hope you understood the concept of supernode here. Supernode simply means combination of two or more than two nodes. Okay. All right. So what we learned today in today's session, we learned the nodal analysis. What is the difference of this nodal analysis with the nodal analysis that we already learned in resistors case? Just that there is no difference. Only thing difference between this and this is the phasor circuit. Phasor circuit means the these resistances are applied here. We have impedances in place of resistances. Otherwise, the concept is same, one and the same. Okay, and same Ohm's law. We use the same Ohm's law that V of voltage is equal to impedance multiplied by current. Okay, and same KCL that we learned in the case of resistor. Okay, and we solved two examples. One example is simple node analysis. Another is based on the concept of super node. Okay, let me end this session here.